capture technologies, the two-track approach that we have adopted, and we go into a bit more detail about the development of the post-combustion capture technology at DPS. Then what I want to also highlight are some of the challenges that we face. Challenges doesn't always need to be a bad thing. It's always good to know the challenges before rather than during a project or at the end of it. Go through some of the technical and non-technical challenges, wrap it up with some concluding remarks, and give you some time for questions. Similar slide that you saw yesterday. I didn't want to give too much of the background of Bruce, and we had that yesterday. So, but the topic that we're talking today is based on the plant business group. Hence, I'm from the plant product innovation team, or it's called plant R&D group. Emissions and electricity generation. This is a slide that from John presented yesterday morning regarding the amount of emissions in million tons of equivalent of oil for different countries, and as you would expect, India and China are leading the way with other countries coming up rapidly. And based on the projections of how it will be produced, coal is and will be for a few years the number one source of fuel. There's nothing behind that. I don't know, this was something that I wanted to get my head around as well, is the amount of installed capacity in India. And this is as recent as last month, 31st of August, from the Ministry of Power website, where it kind of gives you a clear picture that yes, we have 207 gigawatts of installed capacity in India, of which about 55% is coal. So going down on that is going to take a significant amount of work. And if you look at the renewable side, it's about 10%, but generation-wise, we'll probably see it later. As you're probably very aware, nonetheless, what is the anticipated capacity in the 11th plant for India is about 71 gigawatts, and the proposed for the 4th plant is 76 gigawatts. The slide or the picture, I don't know if it's clear. This picture is a old picture. It's not a new one. This was created by one of our strategy guys, I think 5 years ago, when the 11th plant was going on or was in its infancy. So what was interesting for me was looking back. In the 11th plant, anticipated was about 71 gigawatt, and what they expected was about 57 to 76 gigawatts. So which lies in what the projections were. The 12th plant is projected to be 76 gigawatt, and what is provided here is anywhere between 85 and 104. I know it's a bit lower, it's probably because of the reduction in the GDP. So as long as the GDP is up, that's what the projection is going to be. What does that mean by the year 2030, 2035 is additional to the 207 we've got in India, we need another 550 to 730. So that puts into perspective, and if you're going to keep the coal, carbon capture is going to become essential. This is just a slide summarizing what we're trying from the 11th plant summary report from the CEA website. Over the years, what was interesting for me to notice, over the years, if you look at the amount of energy generation growth, that's from 2000 to 2012, as we would have expected, it's constantly going up. So the 550 or 700 number that I talked about might actually be very conservative. They might be much more higher than that. So it's just to put things into perspective. And in the current year, as in 2011, which they summarized on, we have the highest growth of 8.1%. High growth in nuclear. Hydro has improved a lot because of the great monsoon we had. Thermal generation has gone up as well, but not as high as you would have wanted to, because coal shortages, quality of coal issues, and increased hydro and nuclear. So to set the scene, yes, we are going to be looking at coal generation for a while, and if we need to meet the deadlines, we need to at some point think about carbon capture. So it's regarding being more prepared about it rather than worry about it when it's too late. This is kind of an adaptation of the scenarios that Keith presented yesterday, the 2-degree trajectory and the 6-degree scenario. This is from the whole report. What this kind of helps us understand is, if you have a 2-degree scenario, as Keith mentioned, that's the line that you would have taken, right? So going from 30 to the 18, the magic figure that you wanted to go. But things have not progressed as quickly and as faster as you had wanted. So what happens is you are looking at a delay. So what is that delay going to bring in? If that delay goes on till about 2015, you see that you actually won't end up where you want it to be by the 2-degree strategy anyway, even though you are applying the 2-degree strategy from 2015 or from 2017 for that matter. So what that basically means is we have to be more aggressive if we are going to meet those targets in the time scale that we have. Right? And 6-degree trajectory is the business as usual that we mentioned. So after setting the scene, what I would like to hint about is the 2-track scenario that we've adopted at Doosan. We work on both aspects of reducing the carbon. One is increasing the efficiency, so working on efficiency improvements, as well as working on carbon capture technologies. All of them. So when any customer or any client comes to us and says, you know what, this is what we want to do, can you suggest a better technology? This is just going back to one of the questions that was asked yesterday as to which one would you choose if you have to put your money on. It's not just that simple of an answer. If it was, it would have been so much simpler. So it is about addressing all the issues as per the location and the other constraints that you have. So we're working on both of the tracks of improving the efficiency as well as carbon capture technologies, but the goal would be, to reduce the carbon dioxide as much as we can. This was a corporate slide that I thought might be relevant. Is just giving you a feel for, this is very probably resounding what a lot of the speakers have spoken in the past 2 days, is about, based on the evolution of in time, how better we have got the efficiency of the power plant line, and where we are at the moment is with our advanced supercritical boiler 46. We would want to go, we would love to go 50, 55, and which was one of the goals of the EON 50 Plus project that John mentioned yesterday morning, which got suspended. We were part of it, but we were working with EON on that one. Let me get to the bread and butter of carbon capture technologies. How many people in the audience have actually seen this slide, other than the speakers, of course? Just show of hands. Okay. What this slide shows is nothing special. It puts in perspective all the 3 carbon capture technologies and just tries to show you what is the difference. Post-combustion capture is what we'll be talking about today, where you have fuel and air from your power plant line, and you get your flue gas, you separate the CO2 out and send it to storage. Pre-combustion, what Francisco spoke about yesterday, and Ralph Joe spoke from Siemens about it as well. That's the second technology. The third one is oxy-fuel, which I spoke about yesterday. So these technologies are what they are because of the place where separation happens. That's why it's called as pre, post, or oxy. That's the whole idea. Just wanted to touch base on, because you've seen enough about the IGCC and oxy, and I'll go in a bit more detail about the post-combustion capture. Is all these technologies are being evaluated by various technology developers, because everybody likes their product well. So if you go and talk to a particular company who's developing IGCC, they're going to say, yep, that's the best technology, it gives you this, it gives you that. Go and talk to another one who's developing oxy-fuel, that's what they're excited to To be very honest with you, there is no one clear winner in any of it. It all depends on different strategies that we have to take in. And one of the main things that comes into picture is scale up. Scale up is not a very simple. It does take significant experience to actually scale up a plant. Go into detail, post-combustion capture technology. What you have in the schematic is the boiler island going through your FGD. Then you have a CO2 absorber, where you absorb the CO2 from your flue gas. Then you go to a stripper, so you remove the CO2 out. So you strip the CO2, and the off gas is taken out from the absorber, and the CO2 product is taken out from the stripper. Let me just leave it at that for now. I'll go into more detail of that process in a bit. What I want to just touch base on, very resounding back to what Ralph mentioned yesterday about post-combustion capture technologies, is they're not new. They've been used for decades in petroleum industry as amine sweeping pumps. And they're being used even now, even today, using MEA. The only difference is in a petroleum plant, you don't have an issue about how much energy you have to use to strip your CO2 because there is abundance of it. But in a power plant, it is the most critical element. So you want to reduce or keep it as low as possible so you can sell electricity. That's the whole goal. So based on that, let me just go ahead and give you a kind of more detailed description of the process. The flue gas coming in from your FGD of your main plant, goes through a booster fan because you need to drive your flue gas through your absorber column, and the absorber column is going to have pressure drops. So you have a booster fan, and after the booster fan, you've got a cooler, which is typically a direct contact cooler with water to reduce the temperature of your flue gas to make it cold enough to help the absorption to happen. The absorption column varies in size. I'll talk about that when we're talking about scalability issues later. But what it has is basically the pack column with the choice of packing that you choose, which you think is the most beneficial. And the solvent basically comes through the top of the column. The flue gas goes from the bottom of the column, so it's a counter-current mechanism where your solvent strips your CO2 out or absorbs your CO2 out, and the flue gas, if you avoid the CO2, goes to a water wash section, which basically is to remove any liquid entrainment that you might have from the solvent. And then you have a demister section as well to remove any moisture or any other solvent particles that you might have, and the off gas goes off to your stack. The rich solvent, the reason it's called a rich solvent is because it's rich in CO2. So when I say anything about a rich solvent, that's rich in CO2. So what you do is your rich solvent, which is about 50 degrees C, goes through your lean rich heat exchanger. What the lean rich heat exchanger does is it basically provides you with better heat integration options. The reason for it is your stripper is being operated at about 120, 125 degrees C. So the solvent that gets stripped of the CO2 is going to come back to the absorber, but you need to cool it anyway. You need to heat the liquid. You need to cool the liquid. So what would you do? Stick it into a heat exchanger. Well, I wish it was that simple, but it is either one or bank or an array or a different kind of design of the heat exchanger that you have. And the rich solvent goes into your stripper column, and heat is provided in the form of low pressure steam into the deboiler. The solvent circulates back, and the CO2, the pressure of the whole system is going to be about 1.2, 1.3 bar gauge, nothing major. So if you look at your steam tables, water at 1 bar gauge, it has about 60% of water in it. So the stream that's coming out from here has 60% water and 30% CO2. So the first step is you need to condense at least some of the water out. Then you go into compression, which is a multi-stage compression process with compression, condensation, compression, condensation in series, so that you get to your purity levels that you want, 97, 99%, whatever your customer needs, because you're going to sell CO2 at the end of the day. Okay. Another point that I want to mention is after the booster fan and before the DCC, for an amine solvent scrubbing system, you would typically have another small FGD. It's called an FGD polisher. The reason is it's not doing as much work as an FGD, but it's actually reducing the amount of SOx that's present in your flue gas, because SOx is a problem for the solvent because it contaminates the solvent, it degrades it. So you reduce the concentration of SOx by an order of magnitude in the FGD polisher. There are other solvents that you can use which don't need an FGD polisher. We'll talk about that at the end when I talk about the second generation technologies that we've looked at. So, in effect, what comes out from your plant? You have nitrogen and a CO2 mixture going in, nitrogen predominantly coming out from your off gas, and your CO2 coming out from your product gas or your stripper product. This basically is just to give you a chemical representation of how the reaction progresses. And the amine, you need 2 moles of amine to capture 1 mole of CO2. So when people talk about loading of the solvent, that's what they're talking about. How many moles of CO2 can a mole of solvent take? So if you have 1 mole of the solvent, you can have half a mole of CO2. So when people talk about NEA specifically, it's 2 to 1. So the maximum amount of loaded solvent you can get is 0.5. Here is the minimum you got. When you strip it based on how much you strip the solvent out, you get anywhere between 0.2 and 0.3. Different people like it. Just to give you a small snapshot of the summary of the technology. As I said yesterday, the carbon capture industry is new because it's putting all the elements from the different aspects of different commercial plants that's already there. So it has all the components which are all tried and tested. It can be retrofitted to any plants. Has no problem with fuel change. It has already been demonstrated in a pilot scale as well as demonstration scale. So just need to go bigger. Just want to give you a very, very detailed discussion about what is the development of post-combustion capture that we're doing at Tucson. Part of this section of slides might be something that Mr. Jawahar and all of you guys must have seen when you came up to the intro. I think they gave you a presentation at that time. Doesn't have anything. Okay. Like I gave you a heritage for the boiler side of our business. What I wanted to also give you is a feel for our post-combustion capture heritage as well. Yesterday I spoke to you about oxy-fuel that we've been working from 1992 till now. We're waiting on the demo and commercialization for 2020. For post-combustion capture technology, what we have done is we have bought a stake in one of the companies that have been doing enhanced oil or carbon capture for enhanced oil recovery for a large time, and we basically licensed the technology from them. And from the time that we licensed the technology, we've become collaborators. So what we actually do is we do any of the development work that happens, coming up with new solvents, coming up with new processes, new heat integration options to reduce your overall energy requirement. Everything we've been working together, so it becomes our product as well. And the way we've been growing from then is, I'll show you a bit. The ERCF that I talked about yesterday, it was a small plant where we did a proof of concept. For oxy-fuel, what we thought was, there's no point leaving that just sitting and collecting dust. So we converted that into a PCC demonstration facility. And we've been doing feeds and working on demos for Ferrybridge, doing feeds for various commercial offerings. I'll just touch base on that very briefly. So this is just one of the slides from our HTC guys, HTC Pure Energy personnel. They have been around for about 25-30 years working on carbon capture for enhanced oil recovery. In the Canada area, where enhanced oil recovery is the money-making business, and they have developed very sophisticated mechanisms of reducing the energy consumption needed for the region. regeneration, and they're also developing solvents. So solvent is kind of the main thing that works, that holds most of the value, and so that is their core IP, if you will. And they have been working on different sizes of plants up to 800 tons a day. Tons a day, does that sound something similar to what I spoke about yesterday? Can somebody just tell me how much is 1 megawatt per ton a day? You know, a rule of thumb that we just talked about yesterday. 20. 1 megawatt is roughly 20 tons a day of either, if you use it in oxy, it's 20 tons a day of oxygen. If you talk in post-combustion capture, it's 20 tons a day of CO2. So it's kind of, it works in the same way because you need 1 mole of carbon and 1 mole of oxygen to form CO2. So it works pretty nice. Okay, next slide. This is just to show when you're working with chemical processes where you need, and when you're looking for big scale applications like what we're looking for as carbon capture in a power plant, then you end up like 500 megawatt plant, you end up dealing with 3 million kilograms of flue gas per hour. If you're looking at this kind of volumes, you need to look at a large quantity of solvent as well, and you need to look at a large quantity of plant size as well. So what we've been working on is trying to get the supply chain as well. So when we are developing ourselves, you're pushing the supply chain along with us. So when we get something ready, everything is in hand. You don't have to go and find something, you don't have to go and find things. So you can actually execute it very, very quickly. And Huntsman has been our collaborator for a very long time, and we've been working on a program with them as well on a development agreement. Just wanted to give you a feel for the demonstration projects, or I would probably call them test facilities to be more appropriate. What we have is the International Test Center that's in Canada, which is a 1 ton a day facility, which was opened in 2003. So that was one of the small ones that was done a long time ago, which is from HTC's books. Boundary Dam, it's not the big Boundary Dam plant, it's the Boundary Dam pilot plant, which is a 4 ton a day facility. So to replicate this one, we can't always be traveling to Canada just go and do a test, can we? Because we are in UK. So we have our own 1 ton a day test facility where we do most of our solvent and regeneration, etc. tests, the whole. And we've been working on both coal flue gas and natural gas flue gas. So we know what we're looking for. There's no surprises. And then this is probably our demonstration scale, which is Heritage, which is 100 ton a day. So it would equate to 5 megawatt electric scale of a power plant. It's located in the UK. It's connected directly to a power plant. We take slipstream, basically 1% flue gas flow from one of the main units, which has an FGD, and we perform our testing on that one. It's been operational for a while now. Guys from FlexStep have been there for a visit, so we organize different visits for other personnel as well. Let me know if anybody's interested. I think you're in the UK at some point of time. I'll talk about that in a bit more detail after a few seconds. The ERCF is, as you saw yesterday as well, it's a 160 kilowatt combustion test facility. And what we have is, it has a burner, it has a coal and a gas burner, which can be interchanged. We have a fuel to burn, so we don't do tests on simulated flue gas that a lot of people like to do. We work on the real flue gas, so because there are a lot of problems that are associated with having particulates. If you have a high sulfur coal, such as I think we find Williamson coal, which is high sulfur coal, you have problems with the heating plant. So what we're trying to do is, for every scenario that we can have, we burn the right fuel so that you can expect the right behavior of flue gas. And if you know the right behavior of flue gas, the right composition of flue gas, you can design your process accurately without any problems that you'll foresee. We have an FGD polisher that I mentioned before installed on this one because it's a test facility. We want things to be as clean as they can. Just to give you dimensions of the plant, we've got an absorber column which is about 10-inch diameter, not very big enough. It's about 8 to 9 meters. It's 10 meters tall. We've got a stripper column which is about 8-inch diameter. It's 8 meters tall. We've got a water wash section. We've got all the required heat exchange. So basically, when we run a test on the ERTF, which is a small rig, it doesn't replicate, but it kind of mimics the behavior of what we expect on the real plant. And when we design Ferrybridge or when we design any other plant after that, what we do is we have another solvent development lab or a PCC lab as well. So any new development that people say, oh, you can try this, it will reduce your energy consumption. So what we do is we try the lab, if it works, if it has any economic merit, we put it on the ERTF. And the ERTF, we've also had different people or different solvent manufacturers come and ask, oh, can we actually try a solvent on your system? So fine, go ahead. So it's that kind of approach that we have. So once we've tested it on this one, then we move on to Ferrybridge, which is our bigger toy at the moment. And then whatever happens after that, whatever we put together, it will get transferred. So there is knowledge and technology transfer all over, but that is what you need when you're scaling up. Just wanted to give you a feel for the energy consumption. This slide is basically the structure of the ERTF. When you look at it from the product, you can see the solvent storage tanks, etc. at the bottom. We've got a bund in there just in case you have any solvent leaks, etc. But it's pretty well contained. When we do RS2 is our current commercial offering for a solvent, so to speak. It is a blend of amines. It's not just MEA. MEA is something that people like to start doing for PCC work because it's been used for a very long time. So when you test MEA on your plant, what you're basically doing is you're validating the design of your plant. So if your plant actually works on the same lines of energy of regeneration for MEA, then what this will give you is what you'll see on a big plant. That's the kind of analogy that goes when people test with MEA. This is just want to show you some of the best results we've got. Is for RH2 on a cold flue gas, the energy consumption is less than 2.5 gigajoules per ton. And for gas, similar to CCGT flue gas, the energy consumption is about less than 1.4 kilograms steam or less than 3 gigajoules. I don't know if you had a chance of noticing when Raj spoke yesterday the differences between cold flue gas and gas flue gas. In your cold flue gas, you've got about 14% of CO2. So capturing 90% of that is you have a very good chance. But when you're working with CCGT flue gas, where you have anywhere between 4.5 to 6% CO2, capturing 90% is going to take more work. So you're going to need more energy. And luckily with the solvent that we've got, we need a little more energy, not too much, 15% more, which is actually pretty good. What do we use the ERTF for? As I said, we use it for optimizing the process, reduce solvent, energy, etc. But at the same time, what we also do is, because of concerns, environmental concerns of emissions, etc., we work on reducing the emissions to the environment, trying to minimize it as much as we can. And whatever we learn, we actually implement it on the plants that we're working on. And the other main thing that we also use our ERTF for is supporting commercial bids. Because now that we've got Ferrybridge is not our project, it is a collaborative project. This is our project, so when we want to sell PCC, we want to demonstrate it on our plant. So that's what we use this one primarily as well for, is any client comes up and says, okay, can you do a feed study for 4,000 ton a day plant or 6,000 tons a day plant? We actually replicate those conditions here based on the flue gas composition and the solvent that they use and show them live in the control panel or in the control station what energy are they looking at. Because as John rightly or wrongly pointed out, not a lot of people trust the technology developer because they show any number that they want, which is a problem that we face, but we are trying to be as open and honest about it. Ferrybridge. That's the schematic of the Ferrybridge plant. What you see here is That's the flue gas coming. That's the flue gas coming from the power plant, the one on the left, goes through your FGD, boost fan, your DCC, into your absorber column. Yeah. After your absorber column, you've got the water wash section. The flue gas, the off gas, basically goes out. Your solvent comes into the absorber column, goes through your section of leverage heat exchangers, your your stripper, and then what you have in this plant is the CO2 product gas is technically supposed to be taken away for compression and storage. But for this plant, because of their facility, what we're doing is you're taking the CO2 product and mixing it back in the off gas. So the composition of the flue gas coming here will be the same as the composition of flue gas going there. So for the sake of the power plant, it doesn't have a PCC unit on it. Right? So it doesn't have a PCC unit on it. And what does, because the test facility and because we have only 100 tons a day of CO2, that's not a lot of CO2 to actually send for transport and storage. So by doing this, what we found as a benefit was, the differences in the composition of the flue gas that goes out tells you what is the stuff that it takes away. So any solvent or any other contaminants that you have, we monitor it there as well. So, and believe me, this plant is kitted out every inch of it, temperature, pressure, density, different kind of gas analysis equipment, liquid analysis equipment. The reason is we want data. When we try to design this plant, we don't want to base it on a hunch. If we do this, we want to actually match it where we can exactly where it is. Only then you'll be able to find out, because there is always a problem with not enough data. I have to acknowledge all our project partners, very rich. Our four main partners are the government, one, which is Department of Energy and Climate Change, including some of our local funding bodies like Mountain Way, Yorkshire Council, etc. And then SSE and Vattenfall, who are the power plant utilities, and ourselves, and along with TSD, which works very closely with DEC as well. So the project's funded by all of them, not by one single body, it's funded by all of them. The plant is a 100-ton day plant, as I told you earlier, and we take 1% of the flue gas from a 500 megawatt unit in Peribridge. And it is a 2-year program. We started early this year, and it is scheduled to finish in December 2013, when we finish our testing program. We are running with MEA at the moment. After that, we'll test the plant on RS2, and then we have another solvent that we're developing, which will be the advanced solvent that we'll test in the later part of 2013. The thing was, as I mentioned with a few people when we were discussing, it was a fast-track build. And when I mean a fast-track build, from the time the first shovel hit the ground till we actually gave the plant, handed over to SSE, it literally took 16 months. The other plants, similar size or slightly smaller size in different parts of the world, have taken about 2.5 years, 3.5 years easy. And they come over to visit the plant, and that's the one thing there is. That's a very quick setup. So because of that, we've had a lot of troubles as well, but we'll try to iron them out as and when they show up. And that is the main critical part of lessons learned. And these lessons learned that we do will get incorporated to all our future projects or designs. Just to give you a geographical location for where Peribridge is, that's the UK, in case you want to guess. That's the Peribridge plant from a Google map view. And what you're seeing there, that section that you see, the B-marked section, that is the footprint of the post-combustion capture plant that we built. And the picture on the left is basically showing you, in the background you can see the stacks from the power plant with the columns, the absorber column and the stripper column. And in the background you can see the FGD polisher, the DCC, etc. Probably captures a better picture later. As is the case with any of the collaborative projects or the way we work with different parties in Busan, we always have universities on board. purely for public dissemination of results. So for Ferrybridge, what we did was we chose 4 universities who've been working with us for a long time on carbon capture development, and we provided them with the financial assistance and working time on Ferrybridge to learn the process. And their projects, if you look at the titles of them, or that's not going to tell you much, but the projects are oriented in such a way that they do something different from what is already being done. So it is a learning experience for the students as well as it's a learning experience for all the project partners and the technology. So we've got 4 main universities who have been working on the PhD projects: University of Nottingham, Leeds, Sheffield, and Edinburgh. Other than just the PhD projects working in supervision, what we also do is we conduct a lot of different public or university outreach programs. One of them, or a few of them, are we arrange one-day visits to pretty much any of the universities that ask us that we want to come and visit the site. We want to show the students how carbon capture is done. We do that we've done it for these universities, and now we've done it for 8 universities. We give them the background about what the power station is, because a lot of these people haven't seen a power station. Forget about the carbon capture plant, not seen a power station. So we take them on a tour of the power station for half a day, and then a tour of the carbon capture unit. So it gives them some perspective as well. The second one is for a bit more qualified personnel, which is MS, PhD, and postdocs, etc., because they've been working on this technology. So what we do is we give them 1 month secondments. So we give them 1 month of working time on site. So they can come to site, they can do whatever they want, they can work along with our operators who are there, learn from them. And what we ask them to do is ask them to do a mini project for a month, something that is of interest to them, so that they get into it, they get more interested in it. And then the other aspect, what we do is we do an industrial awareness module. What this is basically for SSE and for us is to give the universities a feel for who are the companies who are working on it and how are they working on it. So for first half of the week, they come up to Renfrew, they do the tours of our labs, they do tours of our test facilities, go through discussions, they do some safety exercises. We take them through what are the safety exercises that we do, risk assessments, teach them about hazard studies, why do you do a hazard, etc. And then they go down to SSE's plant and have a tour of the plant, and then they get more interested in working on that plant. Other than that, there are 2 other aspects of involvement from academia. Is one, what we do is University of Leeds is taking the lead on it, is supporting them. There's a 5-day CPD course, is what it's called. It's a continuous professional development course. So people from the industry, people from anywhere, general public, can actually enroll into the course, learn about it, and when they learn about it, all that material that's in there is about Ferrybridge. Yeah? And then at the moment that we have plans of actually moving that as a permanent course in University of Strathclyde for a master's course. The other thing that we do is invite a lot of industrial research organizations, UK, worldwide, to come and visit the plant. Whoever is interested, they contact us and they say, is this date good for us, and we try to stay within it. That's the PR bit, but now looking at the more detailed and testing part. How will we execute this project? Any project that we need to execute needs to be done in a phase, or the way we follow it to be executed in work packages. So the first work section was simulation and modeling, which we need to do because it's a chemical process, we need to do chemical process simulation. And then you apply the design rules and your design aspects to create your engineering designs, P&Ls, PFDs, operational philosophy, all the requisite. And then you go into your layout and modeling. Then comes the most interesting part, which is column and other equipment fabrication, delivery, construction, commissioning, and then testing program, which is where we are at. What are the key parameters that we look at Ferrybridge? Based on what I've spoken, I think you can probably fill up the gaps of what I'm talking about. We look at different capture rates. Are we capturing 90%? How much energy does it take? Are we capturing 85%? How less energy does it take? Different aspects of the process, so that you can investigate it absolutely to its bare bones and find out where the nooks and crannies are, so you know exactly if something goes wrong, what's going to happen at the end of the day. Because at the end of the day, for the power plant operator, all he cares about is the reading that comes on his screen. How many megawatts have I sold out? If he's done 90% and he has a number in mind, if it goes down, he pays attention to the national grid, which he doesn't want to. So it's very critical to understand each and every part of it. So you know what you're looking for. Other main parts are, as I mentioned earlier, degradation products. Are they going into the atmosphere? Are they getting into the wastewater or into the cooling water circuit? How, why, what can we do to actually reduce them or avoid them altogether? Stuff like that. Different process configurations to optimize thermal integration. The other thing that we've kind of included in this project is also material testing. Because I don't know if a lot of people are aware, amines don't like carbon steel. They literally eat through it. So these amine capture or amine sweeping plants are made of stainless steel, 316L. So you can understand how expensive they are. So what we are trying to do is what we have another in-house development project that looks at different or alternative materials which are low cost but still have the same resistance and stability of 316L, and we try to see if those can be used. So what we've done in the plant, I'll show some pictures later, is we've cut piping sections into spools and replaced them with alternative material spools, and we take them out in the middle when we have an outage or maintenance time, and then we